What if we were wrong about black holes? Not just a little wrong, not at the edges, but right at the very center, at the one place in the universe where our physics falls silent and the equations scream at us in shattered mathematics. For decades, we have told the story of black holes with certainty. A dying star collapses, gravity wins, a singularity forms, an infinitely dense point where space, time, and all known laws of physics simply cease to exist. But what if nothing infinite exists in nature? What if the universe, in its elegant brutality, refuses to permit true singularities, and instead builds something else, something stranger, something that from the outside looks almost identical to a black hole, but in its interior is made of the very fabric of empty space, an object called a gravistar. In 2001, physicists Powell Mazur of the University of South Carolina and Emil Motola of Los Alamos National Laboratory published a paper that quietly detonated a bomb inside theoretical astrophysics. They were not trying to disprove black holes. They were trying to solve something far more uncomfortable, a problem that physicists had been tiptoeing around for 30 years, like a crack in a bridge they still had to cross every day. That problem is called the singularity. When general relativity describes the gravitational collapse of a massive star, the mathematics produces something monstrous, a point of infinite density, infinite curvature, infinite everything. And physicists know what infinity in an equation means. It means this theory has failed. Something is missing. Mazur and Motola asked what quantum mechanics has to say about the moment of collapse, at the threshold where a black hole would normally form. The answer was extraordinary. The interior of a collapsing star should undergo a phase transition, the same kind of dramatic, sudden transformation that turns liquid water into ice. Except instead of frozen water, the very structure of space-time would freeze into a gravitational vacuum condensate. The result? No singularity, a gravistar. Its structure resembles nothing in our catalog of cosmic objects, a thin shell of unimaginably dense exotic matter, an interior filled not with stellar material, but with dark energy, the same repulsive energy that accelerates the expansion of the universe, held in perfect equilibrium by the gravitational pressure of the shell. From the outside, a gravistar looks practically identical to a black hole for any distant observer. The same mass, the same gravity, the same bending of light. But this realization immediately raised a deeper question. Can we even tell them apart? Fact 1. In April 2019, the Event Horizon Telescope, an array of radio antennas the size of a planet linked across 4 continents, captured the first image of the object at the center of galaxy M87. It showed exactly what general relativity predicted: a glowing ring of superheated plasma and a central dark region, a shadow. The key detail: the instrument photographed the shape of gravity around an enormous, dark, compact mass. It did not photograph a singularity. A gravistar of the same mass would cast a nearly identical shadow. Within the current resolution, both objects are observationally indistinguishable. Fact 2. In September 2015, the LIGO detectors registered the first gravitational wave signal in human history, the merger of 2 compact objects approximately 1.3 billion light-years away. Physicists Vitor Cardoso and Paolo Pani pointed out something remarkable. A gravistar has an interior capable of reflecting gravitational waves back outward and would therefore produce a subtly different pattern of echoes than a black hole. Hints of such echoes were recorded in the LIGO data. Just hints, not confirmation, but enough for physicists to sharpen their pencils. Fact 3. Black holes are bound up with the information paradox. Quantum mechanics insists that information can never be destroyed, yet black holes apparently swallow it beyond the event horizon and eventually evaporate without leaving anything behind. This paradox has troubled theoretical physics for 50 years without an agreed resolution. Gravistars dissolve it entirely. Without an event horizon or singularity, information is never trapped or lost. The crisis simply does not arise. Consider what a gravistar truly is at its core. Its interior is filled with a phase of spacetime behaving like dark energy, the mysterious repulsive energy making up approximately 68% of the total energy content of the observable universe, which is currently driving galaxies apart at an ever-increasing rate. That is not a coincidence physicists would overlook. What if the dark energy permeating all of space and the vacuum energy inside gravastars are the same phenomenon? What if every object we classify as a massive black hole is a reservoir of dark energy, sealed inside a quantum shell, distributed throughout the universe like nodes in a cosmic web? The evolution of galaxies, the rate of cosmic expansion, the ultimate fate of the universe, all of it would require reassessment. We have the tools to look more closely. The LISA mission, a gravitational wave detector deployed in space with arm lengths of 2.5 million kilometers planned for 2035, will be capable of detecting the subtle echoes that distinguish a gravastar's interior from a true black hole. The Event Horizon Telescope, meanwhile, continues to improve its resolution. The precise shape of the photon ring around Sagittarius A star could reveal subtle deviations from pure black hole geometry. Every merger we detect, every shadow we image, every echo we hear, or do not hear, adds a data point to a question we are only now learning to ask correctly. To understand why gravastars are theoretically compelling and genuinely controversial, we must see the battlefield on which the two greatest theories in physics have been at war for an entire century. General relativity describes gravity as the curvature of spacetime and is extraordinarily accurate at large scales. But it admits singularities, even though they are the very place where the theory destroys itself. Quantum mechanics governs matter and energy at the smallest scales and absolutely forbids singularities. Energy is always finite. Infinities are artifacts that must be removed. Gravastars represent one possible answer to the deepest question in physics. What happens when both theories are simultaneously true? Alternatives exist. Fuzzballs from string theory, replacing the singularity with a tangled knot of fundamental strings, firewalls that incinerate infalling matter at the event horizon. Gravastars occupy a specific, testable position. They make concrete predictions about gravitational wave echoes and about a surface boundary instead of a true horizon. Every prediction is, in principle, falsifiable. We know that at the centers of galaxies sits something enormous, dark, and gravitationally monstrous. We have imaged its shadow. We have heard its collisions ring across 1 billion light-years of spacetime. The observations are real and extraordinary. What we do not yet know, what our instruments have not yet resolved, is what that object truly is in its interior. Whether it conceals a singularity where physics fails and infinity reigns, or whether the universe, in the final moment of collapse, invokes its deepest quantum laws and builds a shell of exotic matter around a bubble of dark energy, an object that from the outside looks like a black hole, but at its center contains not destruction, but a phase of space itself. Gravastars may not be real. The evidence is suggestive, not conclusive. But the questions they force us to ask are among the most important in science. Can nature truly produce infinities? Is information sacred? And what, in the end, does the universe do when it runs out of room? We do not yet have the answers, but we have LISA launching in 2035. We have gravitational wave detectors growing more sensitive every year. And we have a species that has never, not once in its history, looked upon an unanswered question and chosen to look away. The journey continues.